Hi, my name is Callum Gerrigan, and my dissertation is titled Electrogoniometer Application, and today I'll be presenting my specification and proposed design, and my supervisor is Professor Lejic. Just to give a brief background of the application, essentially what the app does is it measures range of motion of angles, and measuring range of motion is important in the clinical setting. Measurements need to be accurate, especially when prescribing treatment to individuals with pathological movement. This is also important for patients returning from an operation and needing reevaluation. This app can be used as a readily available diagnostic tool at your fingertips to evaluate a patient's hamstring tightness and range of motion. And essentially, the phone can be situated at an unambiguous position. The angle is calculated by taking the difference of the device's initial angular position from the second angular position. I also released this application to the Google Play Store, and the first release was on September 7, 2021, and approximately has 8,229 downloads worldwide, and there's about 28 reviews in total. A cool aspect of the Google Play Store is that it gives a store listing conversion analysis. This is basically the number of impressions of people exposed to the product page to the number of users who installed the app from the referral. And having these analytics from the Google Play Store will help with implementing the localization of the app by supporting multiple languages. By providing the insight of which countries have downloaded the app, we can prioritize these languages listed here, such as Portuguese, Hindi, Spanish, Italian, and French. For the project description, the primary goal is to enhance the electrogoniometer app, making it more accessible and user-friendly. I will focus on localization, data analytics, visualization, and GDPR compliance to safeguard user data. Additionally, I will conduct a comprehensive study to compare the app's accuracy with the gold standard goniometer and an image-based goniometry method, further establishing its potential as a medical diagnostic tool. This study will advance the understanding of the app's accuracy and potentially revolutionizing joint mobility measurement. The overall impact of the project extends to the fields of data science and computer science in healthcare, leading to a comprehensive and accurate electrogoniometer app and evaluating its effectiveness as a medical diagnostic tool. For the comparative study, I will be recruiting a sufficient number of participants to the study. The popliteal angle will be the angle measured for all participants. The popliteal angle is an essential assessment for conditions like cerebral palsy and hamstring tightness. The popliteal angle is measured as the angle between the thigh and the shank, which is the tibia, relative to full extension, where 0 degrees is equivalent to full extension when the hip is flexed at 90 degrees as the patient is in a supine position, which means lying on their back. Both legs will be used to measure the popliteal angle to provide more data for the study, and each leg will be measured in the morning and the afternoon. This is an important aspect of the study because as you move throughout the day, you become more stretched and more flexible, so it's important to involve this into the comparative study. 3 measurement methods will be used to measure the popliteal angle, and the accuracy of the electrogoniometer application will be compared to the other measurement methods to determine if the app is interchangeable in a clinical setting. And I will be performing several statistical analyses to see if there's any validation between the other methods compared to the electrogoniometer and see if it's interchangeable. The first method that the app will be compared to is the gold standard goniometer method, and it's also called the universal goniometer, and it's the gold standard for assessing range of motion. A goniometer is essentially a protractor with arms extending from it, 2 arms as you can see in the photo. And range of motion is a crucial indicator of flexibility encompassing ligaments, tendons, muscles, bones, and joints. It plays a vital role in assessing overall fitness levels and identifying potential injuries or damage. Therefore, testing range of motion is of utmost importance in gauging physical well-being and ensuring proper health assessment. The second method is the image-based goniometry method. It's developed by Professor Gabor Barton, who is a professor at Liverpool John Moores University. He developed this application in the programming language Delphi. And essentially, you take a photo and upload it to the application. And as you can see in this photo, The popliteal angle is measured by 3 goniometer overlays, one on the hip, one on the knee, and one on the ankle joint, resulting in calculating the popliteal angle. And lastly, my method, which is the electrogoniometer method, was developed in the language Java in Android Studio, and the phone can be situated at an unambiguous position. The angle is calculated by taking the difference of the device's initial angular position from the second angular position. So as you can see, it's on the thigh, and then it's on the shank, which is the tibia, resulting in calculating the popliteal angle by taking the difference of the two positions. For the aims and objectives, the aim is to enhance and improve the smartphone-based electrogoniometer application, and to make it more accessible, user-friendly, and secure. And then, as I mentioned before, I'm going to conduct a comparative study between the improved electrogoniometer application and the gold standard goniometer diagnostic tool, as well as the image-based goniometry method within a medical setting to evaluate accuracy and interchangeability. And for the objectives encompass accessibility and localization, secure authentication, data analytics, and GDPR compliance, and documentation, and deployment to the Google Play Store. By achieving these goals, I intend to create a comprehensive electrogoniometer app that benefits a wider audience. For the key literature and background reading, there were several key studies and research papers that were explored to inform the design and development decisions for this project. These studies listed here are very important studies that basically explain how the popliteal angle is measured in a medical setting, and a lot of doctors have presented their findings in these studies. I've also found some key papers that go over the objectives that I mentioned, which were the accessibility and localization, secure authentication, data analytics, and GDPR compliance, which is what these papers basically explain. For the development and implementation, I created a diagram in the Lucid Chart tool, which is a tool that develops diagrams for applications, and it basically just shows each activity page of the electrogoniometer application. I also created a UML diagram for the key application components. As you can see, all the objectives of what I want to implement to the app are present in the diagram, and all the components lead back into the application. This is also a brief, simple version of the pseudocode. The main pseudocode of how the goniometer measurement, like how it is used and how it was developed, is in the PDF file. This is just a simplified version of the pseudocode. And I also chose Android Studio and Java as the primary development tools for their efficiency, rich set of features, and extensive developer support. And the pseudocode and the machine learning diagram that I showed before provides a glimpse of the application's functionality and structure, making it a robust tool for recording and analyzing joint angles. This is also a very important aspect of the app. The phone uses Cartesian coordinates, which is the X, Y, and Z, and the Android accelerometer application programming interface gives the X, Y, and Z coordinates. Internally, it is using integration, and the Java code takes these values and converts them from radians to degrees, and the math A102 method provides values between -pi and pi in radians, and the radian value is then converted into degrees by multiplying 180 over pi. This is basically a simple version explanation of how the app records angles. Here's also a user interface mock-up of each activity page. First one is the home page, second is what joint you want to use, and third is the main measurement method, which is the tool. And then fourth is the readings, which is the database in the phone. So it basically stores the data internally, and you can also clear the data or send it to you or a trusted partner that you want to send the information to. And then the about page just basically explains what the app is about and how it's used. And then here is a brief application demo of the app in action. For data sources, there'll be a few sources where data will be extracted from. So obviously from the volunteers, the measurements from the methods that we use, which is the image-based electric goniometer and the goniometer tool. There will be a standardized protocol used, informed consent. The participants will provide informed consent and be informed about the study's purpose, measurements, and data protection measures. GDPR compliance, personal data will be handled according to the GDPR regulations, ensuring privacy and anonymization. Data analysis, collected data will be analyzed and compared to evaluate the accuracy and interchangeability of the electric goniometer application and contributions to the study findings. The data collected will contribute to the study's findings and conclusions. And volunteer participation, the data will be collected only from willing volunteers with ethical considerations and privacy protections in place under the University of Liverpool rules. For testing, the enhanced electric goniometer application will undergo comprehensive testing, including unit testing, integration testing, and user acceptance testing. Ethical considerations are the forefront, ensuring participant consent, privacy, and compliance with GDPR regulations. For evaluation, user feedback and collected data will drive the evaluation process. I aim to assess the app's accuracy, usability, and effectiveness in joint mobility assessment. The results will inform further improvements and refinements to the application. For ethical considerations, throughout the project, ethical practices will be prioritized, including obtaining informed consent, safeguarding privacy, complying with GDPR regulations, and conducting testing with participants' well-being in mind. I also created a Gantt chart, which basically just shows the tasks from research all the way to the end goal, which is the deployment to the Google Play Store. It just shows the timeline of each implementation of the app and how long it will take. And lastly, the risks into contingency plans. In the first column is the risks, and the second is the contingencies. And the main risks of the whole project could be hardware failure, software failure, running out of time, and programming problems. So I just want to say thank you for listening, and I hope you enjoyed. And I have also provided some references at the end of the presentation. Thank you.